This video is part 2 of the Unit 2 review for the test that's coming up. And we're looking here, starting at problem number 8. A train is traveling at 250 kilometers per hour. So we're going to put that here as our known. How fast is that in meters per second? And so we'll put that as the unknown. So there we have our data for the problem. And we're going to have to get this unit of kilometers changed into meters. And to do that, I'm going to do kilometers to meters. There, I know that step. And of course, I'm going to get kilometers to cancel, so I'm putting kilometers in the denominator right here. In the denominator of my beginning measurement, I have time in hours, and I can convert that by putting the hours right up here. And notice if I put the hours upstairs here and downstairs here, they should cancel out. And I'm going to use a conversion factor to minutes. But I need to go clear to seconds. So I'm going to put minutes here and seconds here and use that conversion factor to convert to seconds. So now if I check my units that are here, the unit that's not factored out is meters on the top and seconds on the bottom. So I have my unit here as meters per second. So I do 250 times 1,000 divided by 60, and then divided by 60 again. So with two significant digits, like these two significant digits right there, my answer should have two significant digits, and it appears that we come out in 69 meters per second. So write that out and play with it if you have any questions on it. Moving on to number 9, what we learned about density and the slope of the mass to volume ratio. You know that we had some graphs there. In fact, on your review sheet, the graph is on this page. On my key, I think it's going to be on the next page because we had some formatting issues with that. But we're talking here about a piece of plastic, and you should have seen this piece of plastic in class. It's a small piece of plastic. It has a mass of about just a little over 15 grams, and the volume actually changes from 14.5 when it's cold to 15.5 when it gets warmed up. So what that does is it changes our mass to volume ratio. When it's cold, the mass to volume ratio is 1.04 grams per centimeter cubed. And when the piece of plastic warms up, it expands, and so the mass to volume ratio is 0.974 grams per cubic centimeter. So if we move on to the sketch, we need to be sure that the piece of plastic with the greater slope, that's this one. I'm just going to trace that in here. That is 6A. In other words, if we come back up here, we will see that in part A, the piece of plastic that is colder has a density greater than water. Remember, the density of water here is 1 gram per 1 centimeter cubed. And so this is actually the cold plastic right here, and it sinks because its density is greater than water. So we draw that slope, which is greater than water, above the slope for the water. Now the other piece of plastic has a mass to volume ratio a little less than water, and so its slope is less, which we found out in lab meant it would float. Now, the thing a lot of people are missing as they work on the review sheet, as I've seen them working on it, is they miss this explain part right here. The mass to volume ratio, or density, of warm plastic is less than water. And I've quoted that value here. That's an important thing to do when we're making statements in science, is to quote our data. So it has a slope less than water. The cold form of the plastic has a density, and that should be written in here. Its density, I believe, was 1.04 grams per centimeter cubed, which is greater than water, and so a steeper slope, so it will sink in water. So that's the answer to this question right here. Moving on to number 10. If we multiply these numbers, we get 1.56 times 10 to the 26, and the main point of this is really just to practice that with your calculator. And it's really, for your purposes for this class, it's good to understand how you can do that without a scientific calculator, but it's also good to use that EE button, or in some cases an EXP button, that will help you do that quickly, because you may be needing to do a lot of those kinds of calculations. Similarly, we find that when people start doing a lot of these calculations, if they don't use those two buttons, they have trouble when they're putting this into their calculator, and it may result in getting a positive exponent instead of getting this negative exponent here. So be sure you look at your numbers like this. If you have a number like 259 and you're dividing it by this huge, gigantic number, you know that your answer should be much, much less than 1. A very tiny number, still a positive number, but much less than 1. And make sure that that reflects in your answer here, especially in this exponent. So write the following in scientific notation. Notice here that if I have 1.50, I'm drawing all the significant digits there. That's a sig fig in this case. Times 10 to the negative 3, that this decimal point indicator right here does indicate that my decimal point really is back here 1, 2, 3 places in the negative direction on the number line. So yes, that looks right for that particular conversion. And moving on to B, of course, I'm just going to write the significant digits, 6.23 times 10, and I'm going to move the decimal point from where it actually is, 1, 2, 3, 4, 5 places to get back here, so 6.23 times 10 to the 5. Of course, anytime you see a million, you know that that's like 10 to the 6, but how are you going to show 3 sig figs? Well, that's important here that we can do this with scientific notation, because we can write these and it shows 3 sig figs, and then we can just do times 10 to the 6 to give us an idea of how big the number is, but still show 3 sig figs, as opposed to if we just wrote this, let's see, 10,000, 100,000, a million, that would only have 1 sig fig. So scientific notation really helps us out there. In this problem, we're moving the decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So to get it back to its original location from here, we'd have to move 10 places in the negative direction on the number line. So that seems to match up. Okay, what else have we got here? We're just doing those, writing them as decimal notation. So moving this 5 places in the positive direction on the number line, moving this decimal point 6 places in the negative direction on the number line, and then, of course, some people get confused when they see this because they forget that that's really 1 times 10 to the 6. So here's the 1, and we're moving our decimal point 6 places in the positive direction on the number line. Okay, let's look at number 12, and we must be about done with the review sheet at that point. Number 12 says students use 3 different electronic balances. So we have student A and their measurement, student B and their measurement, student C and their measurement. Now it's also important to notice that this piece of copper they're measuring, it was a standard piece of copper, and we knew from comparing it to other instruments that it was a mass of 23.94 grams. So that's an accepted value that we know is correct. So the students measured that piece of copper, but they got different values for their answers. So which is most precise? Don't forget to explain your answer. And when you're explaining your answer, you should always quote data that you're given to support that answer. Now in this particular case, student C has the most precise measurement. So we've told which is most precise. Now let's explain the answer. There are more significant digits indicating she used a more precise instrument. What was the data? Well, she measured 23.550 grams. That's 5 sig figs. That's more sig figs than the other measurements, which have 3 or 4 sig figs. So yes, good job using a precise instrument. Now, that does not always mean that it's going to be most accurate, because accuracy, when we go to explain our answer, we want to say that accuracy is the closest to the accepted value. And if you look, student A is the most accurate because her measurement is closest to the accepted value. She measured 23.9 grams as opposed to the accepted value that we know is correct of 23.94. So we can see that student A made the most accurate measurement, even though it was not the most precise. Well, if you take some notes, practice some of these problems, go back over your other worksheets, and be ready for this test. Good luck, and we'll see you on test day.